the addition and multiplication operations on this set, then this set also forms a ring. So this is a subring of this. It's just like the concept of a subgroup, that's all. But since we haven't mentioned it formally, we are just mentioning it here. So one can verify that this is a subring of R. The point here is that this is a ring after all. Okay, so that point is going to be used. Okay, now we are going to take any arbitrary element in this ring 3R. Let y equal to 3R belonging to 3R be any element. Then what is y square? Y square is 3R times 3R. You remember that result which tells us that in a ring if we have MA times NB, then that will be MNAB. So this gives us 9R square. Okay, 9R square, right? That 9R square can be written as 6R square plus 3R square. Naturally, but according to what? Do you realize what is going on here? Why is 9R square equal to 6R square plus 3R square? Remember that we are in a general ring. These are not numbers. 9R square is actually this. In this group. And it can be written like this. So by using a laws of exponent, one of the laws of exponent that is available in group theory, this is equal to R square to the power 6 times R square cube. Okay, and this times that we are writing is actually, it is the binary operation that is there. That is, we are not writing anything in its place. When you include the binary operation and in place of writing this you write 6R square, you get 6R square plus 3R square. That's why. If we are not careful about these steps, why they are true, we may easily end up making mistake. Here it just it feels like this should be this is true, but it's not casually true, just like these are numbers. That's not the reason for it to be true. The reason is something else. Okay, now we have proved that 6 times any element in the ring is 0. So this is going to be 0. So we are left with 3R square. But look at this. 3 times x square, x is any element in the ring, is nothing but 3x. So this is equal to 3R. So that is nothing but y. So in the ring 3R, if I take any element and take its square, I get the element back. And this is a condition that was there in one exercise before. Hence, by exercise 4, of section 3.2, 3R is a commutative ring. So this exercise asks us to show that if in a ring the cube of every element is the element itself, then it's a commutative ring. But before that, we came across an exercise where it asks us to show that the ring is a commutative ring if the square of any element is the element itself. That is somewhat more easy than this one. And we are having to use that result here. Okay. So that means, for any x and y in R, we have, can I write it at once, or let me just write it in a few steps. 3x times 3y is equal to 3y times 3x, because 3x and 3y are two elements in 3R, and 3R is a commutative ring, so we can write that equation. Okay, so now what does this imply? This implies 9xy is equal to 9yx using this thing, okay, MANB, or since 6xy will become 0, so we will be left with 3xy and 3yx. 3xy is equal to 3yx. Okay. Then out of nowhere there are some other calculations. Okay, so we let this sit. This will be helpful, but then now something else. Also, x plus y whole cube plus x minus y whole cube is equal to x plus y plus x minus y, and this implies expanding all the powers and doing all the cancellations. After everything is done, ultimately we have an expression like this. 2xy square plus 2yxy. You please do these calculations, okay, and see that this, you actually get this, plus 2y square x is equal to 0. Hence, two y xy square plus 2y square xy plus 2yx. This can be written as 2yx y square plus 2y square xy plus, in place of y we can write y cube, because every element is its cube. And if I use the distributive law and take y common out, I am left with 2xy square plus 2yxy plus 2y square x. But this is equal to 0. So this is 0. And there is one similar calculation. 2xy plus 2y xy square plus 2y square xy. This is equal to 2xy cube plus 2yxy square plus 2y square xy. Now again we take y common out, but from the right hand side using the right distributive law. 2xy square plus 2yxy plus 2y square x. So here we end up with the same expression. So this is also equal to 0. So that means this is 0, this is also 0. And what do we have here? 2yxy square, same term. 2y square xy, 2y square xy. And we have 2yx and 2xy. So using these things and the fact that they are 0 and hence they are equal, these terms get cancelled out and we are left with 2xy equal to 2yx. Okay, in the frenzy of writing these solutions, we have obliterated the perpendicular bisector. I can roughly write a messed up one. Okay, hence these imply 2xy is equal to 2yx. So now we have this 3xy is equal to 3yx and 2xy is equal to 2yx. Hence xy is equal to 3xy minus 2xy. But 3xy is 3yx and 2xy is 2yx. So this is equal to yx. This ultimately gives me that xy is equal to yx. Hence the ring is commutative. So you can see that it seems almost impossible to come up with the solution, but it takes time. And whoever solved this, they had enough time to go through all these things. They failed no one knows how many times, and they ultimately came up with this solution. This is not my solution. Okay, I got it from somewhere else, somewhere on the web. Thus, R is a commutative ring. If you see the final result, the final glory just at once, you think it's impossible. But if you see the long path of all the failures, then you will realize that it's still possible. Only the thing is, it takes time and perseverance. You cannot give up. 2 more exercises are there. Let me just finish. Okay, they are not very lengthy. This will complete this set of exercises. Exercise 20. If R is a ring with unit element 1 and phi is a homomorphism of R onto R prime, prove that phi of 1 is the unit element of R prime. You remember when we defined a homomorphism, we said that a ring homomorphism must respect addition and multiplication, but it's not necessary that it respects unit elements also if the rings contain unit element. However, there we mentioned that there are conditions which ensure that that is the case. That is, the ring unit element in the first ring gets mapped onto the unit element in the second ring, and one such condition is to have the homomorphism onto, then it will happen. So the solution goes like this. Okay, so we have to prove that the image phi of 1, where 1 is the unit element in R, is a unit element in R prime. So if we multiply an arbitrary element of R prime by phi 1 from both sides, I must get that arbitrary element back. So let y belonging to R prime be any element. Now this is where ontoness of phi is required. Since phi is onto, there exists an element x in the domain ring R such that phi of x is equal to y. Thus, if I multiply y by phi of 1, I can write it like this: phi of x, phi of 1. Since phi respects multiplication, this equals x1, but since 1 is a unit element in R and x is an element of R, this is nothing but phi x, which is y. So you get this product as y. And there is one more. And phi 1, it just goes like the previous one. Hence, is the unit element of R prime, sorry, and that completes the solution. And the last exercise. 21. It also is similar. It says that phi of 1 will be the unit element in the range ring, but the conditions are different. If R is a ring with unit element, okay, with unit element 1 and phi is a homomorphism of R into, now it's not given that phi is onto, but the range ring is not just any ring, into an integral domain R prime, then prove that, oh, but there is one more condition, and the kernel of phi is not equal to R. That is, phi is not the zero homomorphism that maps every element of R onto the zero element of R prime. That's not what it is. Then prove that phi of 1 is the unit element of R prime. Now we are immediately going to make use of this one. The kernel of phi is not the entire domain ring. Since I of phi is not equal to R, there exists some element x in R such that phi x is not equal to 0. Such that phi x is not equal to 0. Okay. Then for any element y in R prime, y times phi of 1, phi of 1 or phi of x, oh, it is something else, sorry. 0 is equal to y times phi of x minus y times phi of x. This definitely is true because they are both same, right? Now y times phi of x minus y times, you see, in place of x we can write 1x. We can write because x is equal to 1x, and since phi respects multiplication, so this will be phi of 1 phi of x. Now using the right distributive law, you can take phi x common out. Doing that gives us y minus y phi of 1 times phi of x, and that is equal to 0. Now note this calculation is being done in the ring R prime, and it is given that R prime is an integral domain. Being an integral domain, R prime has no zero divisor, and phi x is non-zero. So this product can be 0 in only one case, when this factor is 0, since R is an integral domain and let us just mention that also, phi x is not equal to 0, we must have this equal to 0, that is y is equal to y times phi of 1. Note one more thing, since R, this is R prime, sorry. Since R prime is an integral domain, it is by definition commutative. Since R prime is commutative, we also have y is equal to phi 1 y, hence phi of 1 acts or is the unit element of R prime. This completes the solution, and it completes this set of exercises at the end of section 3.4. The next section is section 3.5, which discusses ideals and quotient rings in more depth. and there also we have exercises at the end. After that, I think we have the section which involves the field of fractions of an integral domain. We will see those things, but before that we have to go back to function theory in analysis, and as I have already said, I mentioned in my page that I'm going to start group theory, so these things are coming. So with this I end this video. This is me, Lucifer, signing off from the mathematical room. If you are new here, please subscribe to my channel. It helps me out a lot. So with that, I say goodbye. Have a nice night.